Hi, my name is Jory Schossau, and this is my poster presentation on neuroevolution in dynamically changing environments. The driving question is how to get complex richness, like in biology. Now, the assumptions that we're making in this project are that complexity can be reached through open-ended evolution, and that can be reached through ever-changing fitness landscapes. And does it work? Now, of course, all of these can be studied through different hypotheses, but the one that we're studying is ever-changing environments will lead to more complexity and exploration of the fitness landscape. And to quantify this, we use the exploration of the static versus dynamic fitness landscapes. So there are several problems to this, one being that if we allow evolution to evolve too slowly or too simply, that will yield static adaptation. And conversely, if it's too fast or too complex, that will also yield meta-adaptation. And either one of those is not good. It's not what we're trying to study. So we're going to have to sort of thread the evolutionary needle on that one. So what does the environment actually look like? Well, here we've got a robo-mouse in a 2D grid for a foraging task. Now, the world is circumscribed by barriers with random barriers in between, and 4 different random food items are placed in the world. And this is an environment we can call green eggs and ham, because in different scenarios, we have the value of the different foods have different rewards associated with them. But this turned out to be too easy for the agent to solve, so in a new version of this that we call green eggs then ham, we extend this payoff matrix into the temporal dimension such that the current food item yields a reward that is predicated on the previous eaten food item. This means that the best food that you can eat is completely dependent on what you just ate before. Over evolutionary time, we can change these values in the payoff matrix, in the reward matrix. And for instance, this value in the bottom right, we can change according to a fixed schedule. And if we can do that for one item, we can do that for all of them. And this will yield a smoothly changing but unpredictable and hopefully still adaptable fitness landscape. So now that we have the fitness landscape, how do we actually measure what the agents are doing? Well, we can look at their brain. So here is a bunch of states, both hidden states, input states, and output states for the cognitive substrate that is the agent. And from any time point of these states to the next time point of the very same states, any number of logic structures completely under control of evolution might be affecting information in and amongst these states. Now, it is this connection diagram from t to t+1 of the input, hidden, and output states that we can create an adjacency matrix. And any 2 of these adjacency matrices can be compared using the Frobenius distance, which gives us then a quantifiable metric to start measuring for an archive of novelty. We can then put all of these distances between all brains into an archive of novelty as a measure of what the agents have explored in the fitness landscape and how much they've explored. Now, how does this archive work? Well, let's assume we have this example current solutions in the archive that we've already stored, A through D, and we come up with a new solution, N, that we'd like to store. Well, any new solution will be included in the archive if the minimum distance to any of the existing solutions to the new solution is larger than any of the distances between the current solutions, then it will be added. So in this case, it will not be added in that position. However, if, and only for this 2D example, if it's added far out here, then it would be included into the archive. And then the smallest distance one in the archive would be dropped to maintain archive size. Finally, we can take the average distance between all members of the archive as a metric for the solution space discovered, or the coverage. Now, what does this look like when we actually evolve populations in the fitness landscape and measure the coverage of novelty? Well, it turns out that the static and the dynamic fitness landscapes encourage evolution very similarly, which is unlike what we expected. We expected the dynamic environment to encourage better exploration, more rapid or different in some way from this static fitness landscape. And they're not that different. However, future work might entail exploring more environmental change speeds, because here we only explored a single speed, exploring more interaction graph complexity, and perhaps other metrics of exploration. And of course, we may yet still have to thread the evolutionary needle, as it were. Thank you, and let me know if you've got any questions at my poster session.